to go, and I will take. Yes.
Yeah, Jered, you're good to go.
I think that's my cue, right? Hey all, it feels really weird to be giving a presentation to you all without seeing you. Still really happy to be here and on this side of the screen where I'm doing the presentation. And well, as the title already says, I'll be talking today about interaction, specifically in the context of social sidewalk navigation, and more specifically in the context of unpredictable social situations. But before I dive in, first, a really brief bit about me and my background. I studied cognitive AI back in the days where good old-fashioned AI didn't always necessarily include machine learning. Did a PhD in social robotics on social navigation, and I am now working as a postdoc in the design faculty of TU Delft, specifically knowledge and intelligence design. And what for me is a constant is a fascination with people, basically. And there are some amazing things we can do that our machines can't do yet. And I think a good starting point here, and this is actually a shot from the Matrix, but is this amazing human capacity. If you were faced with this crosswalk, somehow you would probably be able to find a way. Even though there's a whole wall of people, somehow the wall would split for you and you could navigate through this whole mass of people. And I think that's quite fascinating and interesting how we actually get that going. And in fact, we even managed to do it in more complicated situations, such as those with kids or dogs with leashes. And in fact, we even managed to do it in situations where everything gets turned on its head and we suddenly have to keep 1.5 meters distance. So there is somehow this amazing human quality to find a way, even if rules change, if we don't know what to expect from other people. And what I would like to be discussing today is how can we translate or at least get robots to fit into that as well when they're navigating. The niche will be specifically within AI, robotics, HRI, social navigation. And slightly more specific, I'm looking into sidewalks. So I know a lot of people within AI tech look into social navigation. I look more specifically into sidewalks, also because I think it's a very interesting sub-niche where you get much closer to the people and the social rules are much more important than the traffic rules. And at the same time, it's also a more safe environment because you cannot kill people by driving over them that easily. So wait, one important disclaimer to give before I dive in further is that most of the things I'll be discussing today are not necessarily new per se. So I might introduce things and concepts that might be quite familiar, and I hope actually that the main point of what I will be doing is perhaps putting them together in a slightly different way that might lead to a nice actionable way to get this working. So to kick off, let's start with a very rough overview of the state of the art in social navigation. I think one of the very first examples is Shaky, but nowadays, and perhaps many people will want to correct me, but I'm just going to try and summarize it this way anyway. Much of the work is based on theories on human social positioning, like proxemics, which is the idea that we should, depending on how close we are to someone, actually take a specific physical distance to them as well. And then those models then have to accommodate things like the fact that humans move, or the fact that humans respond to what the robot is doing. And that leads to very beautiful solutions in terms of path prediction and appropriate quick replanning, both machine learning based and cognitive model based. It also leads to sometimes social navigation being more efficient and effective in controlled settings, such as the warehouses of Amazon, where you can just tell your workers what to do or what not to do. And similarly, there's also beautiful solutions to how humans respond. Not going to go into too much depth there because I have some other things to say about that. And lastly, of course, there is the learning from experts, where we try to somehow take their expertise and replicate that. I think the gap that's currently faced by this state of the art is that in the wild, when you throw your perfect algorithm into the real world, people often turn out to be complex, unpredictable, or dynamic in their reactions, and perhaps most importantly, unique in their needs. So different people might have different needs, even on different days, if they're in a bad mood or a good mood. And I think that raises the very important question, how can we assure socially acceptable navigation in the face of such unpredictable and unknowable social situations? And this is actually, unfortunately, a more relevant question than I would like. I'll read out this tweet for you. It's from Emily Ackerman, or Emily Ackerman, I think is her real name. She, in a wheelchair, was just trapped on Forbes Avenue by one of those delivery robots only days after their independent rollout. She can tell that as long as they continue to operate, they are going to be a major accessibility and safety issue. So what happened here was that these robots roam the streets to make small deliveries. And in this specific case, while she was crossing the street, the robot was stuck in the sidewalk because it saw so many people in its direct environment that it didn't know how to find a safe path. And so it did the second best thing, which is just not move at all. And that was typically a very good solution, but in this specific case, it meant that it blocked the curb, so the low piece of the sidewalk that you use to get back on the street if you're in a wheelchair. And that resulted in quite a big problem for this specific wheelchair user. And there's several more examples where our beautiful algorithms break down when we throw them into the world. There's children harassing mall robots. There is people learning that autonomous cars just stop for them and thus consequently deciding to cross in front of them without stopping. There's office robots being unable to use elevators. And there's actually the whole package of challenges faced by autonomous vehicles that may have led to the current shift from autonomous to automated vehicles. And if we look at the current solutions for these problems, they are a bit of a band-aid. So they are band-aid solutions, I would say. For example, recent tweets seem to indicate that the robot now avoids claiming the whole curb. The Mar robots, I think they did something beautiful there. They predicted the likelihood of harassment, and if a kid was deemed highly likely to harass the robot, it would flee to their parents. The office robot asked for help, and like I already said, we are now moving from autonomous to automated vehicles. And I think all those solutions actually face the same problem again, because people in the world still are complex, unpredictable, and dynamic in their reactions and unique in their needs. So yes, this is a band-aid, and I think it's very important that we make them. But the question I am exploring and that I hope to be discussing with you today is, could we perhaps solve this on a more fundamental level? Can we actually, well, like people do, figure out a way to do this even though we don't know which situations to expect? And I think a very good starting point for answering a question like that is always to look at situations where it goes wrong. And I hope you are all familiar with the Sidewalk Shuffle. And this would be one point where I would really like to see your faces nodding, but that's live at the moment. The Sidewalk Shuffle is when you're walking on the sidewalk and someone is heading in your direction, and you step aside, and at the same time, those people also step aside. So you step to the left and they step to the right, and you're still faced with the same problem, and you step to the right again and they step to the left, and you're still faced with the same problem. And you get that back and forth where you end up having to stop or somehow break out of this loop of adapting to each other at the same time. And I think that's a very interesting point, because it shows it's where our mechanisms break down, and it shows that we apparently are really good at adapting to each other, even though we need some time to do so. And I think that brings me to my main idea or hypothesis, which again is not necessarily new, which is that we are figuring it out as we go. And I think that actually, so not necessarily learning, but just going forward and then failing or succeeding, either way, using that somehow as a way to adapt our behavior and find more suitable behavior on the fly. And I think if we could manage to somehow put that into our robots, we could solve a lot of those situations where we don't know what to expect and still run into problems simply by being able to figure it out. So how can we get that into reality? Well, my proposal actually is pretty straightforward, and it combines something that many of you will probably be familiar with, which is an interaction-focused approach. So we have examples from embodied embedded cognition, action perception feedback loops, reactive robotics, Bratenberg's vehicles, and that's just the tip of the iceberg. There's lots of people advocating for work that focuses on interaction in the actions of a robot. But I propose to couple that to the cues that we give to each other. So, for example, when we are walking on this sidewalk, if we are trying to find a gap that's not just a matter of going and hoping for the best, it's also really looking at people's faces. And it might be that the tall man in the dark sunglasses might be in a bad mood, and you might be heading straight towards him, and he might not be willing at all to get out of your way. And picking up on that, picking up on those cues and using those to adapt, I think is fundamental. So together, that means that I would propose to have the robot pay to the implicit feedback in people's responses to its behavior, and then use that as the basis for finding more suitable behaviors through the interaction. I can talk a bit longer about this, and I will, but actually this is the meat of what I propose. And well, that means that the hypothesis is that responding to people's social feedback cues can find, through the interaction, socially acceptable navigation in the face of unpredictable and unknowable situations. And that means that I envision a situation where if the robot is driving and someone is just not in the mood to get out of its way at all, that then still the robot would be able to sort of detect from their behavior that they're not in the mood to adapt to the robot, and subsequently the robot would adapt more, or perhaps even find a way to convince them to still get out of its way for a bit. That brings us to the next big question, I think, and that's how are we going to make this real? How are we going to do this? First trick in doing that is always to zoom in. So I actually think that this kind of mechanism might be feasible for a lot of interactions we have with physical systems. But to keep things feasible, I zoom in on small mobile robots, such as delivery robots, navigating the sidewalks, and trying to be socially acceptable in terms of time efficiency, safety and comfort, and perception of the robots. And that leads us to a lot of different steps. And to be honest, this is also a bit of an invitation to all of you, both to give thoughts and insights, but also to perhaps connect if you feel that this might be something related to what you're working on. Because I think to make this happen, we need to start with a clean baseline, then find a small and relevant set of feedback cues, small set of behaviors, and use that to somehow explore different interactions. And I think based on the time, yes, I will give you already a quick teaser of the pre-study one, a clean baseline. which is what I've been talking about so far. I think is really focused on the emphasis on how we can somehow let the interaction emerge from our responses to each other. And I think that what that also means specifically for social navigation is that we are somehow often tempted to try our solutions. And the problem that has is that it also immediately gives rise to new emergent behaviors. So, for example, if we have a robot that just tries to stay 1.5 meters away from humans, we get beautifully weird navigation behaviors where it's fleeing from humans, where humans are adapting to the robot and the robot is adapting to them, leading to wobbly paths, deviations. So my step one, the clean baseline, would be what happens actually if we take away all social behaviors from a social navigating robot. So just make a robot that basically ignores all humans. I had started these explorations just before COVID hit. Unfortunately, I won't be able yet to give you full-fledged results. But I did make some cool observations that I do want to share because I hope they will provoke some interesting discussions soon after. And so what we did, we made this small robot. I'm not sure if you can see my mouse, but the small robot you see on the bottom right, and had it drive around. It's actually a cardboard box, so we could relatively safely ignore humans. And we observed when problems actually arose. So just went in without assumptions and started looking at which conflicts does such a robot actually run into and what are the problems we actually need to fix when we start with a clean slate. And I'll share two observations with the very important disclaimer that these are just first observations, not proven results yet, still. So observation one was the robot was driving through the city, apparently on its own. It did stick a bit to the right, but it very much stuck to its own paths, did not slow down, speed up, or deviate from its trajectory for anyone. And this was the city center of Delft, so it wasn't too crowded, but still a decent amount of people was around. And interestingly, to me at least, especially based on all the literature I've read so far, the robot could follow its trajectory completely unimpeded. In fact, people actively did their best to get out of its way. And that wasn't even too noticeable. Some just made very subtle changes in their trajectories. Some of them slowed down just a bit. But at the same time, there were also people who actively steered their walking aids out of the paths to make sure the robot could just keep going. Which I think is quite interesting because it might suggest that our robot, which was very clear and straightforward in its paths, might actually trigger people being more adaptive to the robot. One more observation, and then I hope to move on to the questions soon. In contrast to what I just said, we also noticed that when groups of people were standing still, for example, because they were chatting, if there was enough space to navigate around them, then straight up approaching them, which we had the robot do because, well, it ignored people, somehow that felt to people as if it was engaging with them. So somehow we found there was a big difference between people who were moving and people who were stationary. And I think that's very interesting. So we saw that they engaged with it. They started taking pictures. They seemingly started exploring how they could play with the robots, which very much looked like they were actually teasing the robot and trying to break it. Which I think is, just like the previous one, a very interesting twist on what is already known. Because yes, if you throw your robot out there, making it avoid people, you wouldn't even run into this situation. You would have avoided this problem. but you also fail to see that it arises specifically when people are standing still. And I think that's a very interesting way to go at it. And in fact, what I would really love to do is hear your thoughts on this. And I might have something more to wrap up at the end, but I think this is a very good point to go back to seeing each other and having some questions and some interaction. Because in the end, I think that's the most interesting bit of being here and being here with you. Thank you.
Thank you, Jered. That was great. So, yeah, well, the floor is open for questions. If you want, you can post it in the chat or just ask. Or you could raise your hand. Good. Luciano, you wanted to ask something?
Yeah. Hi, Jered. Thank you. Very interesting work. I have a question actually regarding the social cues. So I understand the next step is to model the social cues with respect from the humans to the robot, and our idea is try to imitate them, that the robot would be doing the same cues to the human, or how do you see this interplay?
I think that's a very interesting in which question, and that means that partially I don't have the full answer yet.
Okay.
I think the first step is actually to understand the cues that humans are using. So not necessarily to mimic them, but to understand and be able to read from people's reactions how they feel about robots. To give one example of that, another observation we made was that sometimes people would deliberately change their path so that it would collide with the robots.
Yeah.
So they would sort of challenge the robot and see what would happen. And I think that's a very interesting cue to pop up. And it would be very relevant for the robot to be able to detect, I think this person might be challenging me. Also because in the end we found that if that happened and the robot just kept going, most of the time people would jump out of the way at the last moment, figuring out, yes, the robot is not going to stop for me. My teasing didn't work. So I think in that respect, the first step is really to detect the cues and use that to change the robot's behavior. But of course, changing the robot's behavior will also result in the robot giving cues to people. And an awareness of that and how to steer that is something that I think we will really have to figure out as we go, because it's such a complex and emerging situation that I find it challenging to make real predictions about what will happen there.
Yeah, I understand. So, but thank you for sharing this. This is a really interesting field. Thank you very much. I think we have one more.
We have the next question from Simeon.
Yep. Hi there. Sorry about some of the background noise. There's some construction work going on here.
Any robots involved?
I'm sorry?
Any robots involved in the construction work?
Oh, man. I don't know. Anyway, my questions kind of relates to what... I mean, obviously, interactions with robots and people does mean interaction, so that's two-directional, bidirectional. So to what extent do you think that we should focus either on the robot avoiding people or maybe the humans getting cues to avoid people? And where do you think the onus lies in that responsibility? So also, while you were presenting, I was thinking at a certain point, so I don't know if you know Star Wars, you know all these droids at certain points where they'll be going in and out, weaving in and out of people. My thought process there is, well, these are droids or robots that are avoiding people and not necessarily the people avoiding them. So seeing that maybe humans were on the street first, should the robots be avoiding people, or is it really this bidirectional interaction you were looking for?
Thank you. Rich question again, which is good, which is why I really enjoy speaking here. And I think it has to be bidirectional in the end. So if our robots would constantly be giving way to people, then they wouldn't be fulfilling their function. And actually, they might be ending up worse. So the example I already gave of the woman getting stuck on the street because the robot was waiting for people in the curb, I think that demonstrates that it might actually be more problematic sometimes to not engage in the interaction and say, oh, I'm subservient, I'll just hold back, rather than actually engaging in it and doing the back and forth. So I would strongly argue that we need to engage in the back and forth and don't have robots always yield to humans, unless perhaps we are on a big starship and there's not that many people around and just a few small robots. But that, of course, still leaves open the question where that balance should fall. So should robots yield most of the time, some of the time, how to basically balance out that taking dominance in the interaction. And again, I think this is something to figure out as we go. I also think it's something that may change. So perhaps at this stage, people are quite willing to accept robots. So all the examples I gave were of people mostly enthusiastic. Oh, there's a robot, cool, new thing. But that might change massively if there is 50 robots on the street and you have to wade your way through them, and you might be less inclined to actually give the robots right of way. And I actually think that might make it more important to listen to the cues and to figure this out based on people's reactions. So not to say, so we're going to sit at 50% of the time the robot will yield, but rather have the robot stay in tune, stay attentive to the way people are responding to it yielding or not, and using that to decide whether or not it should yield. And then perhaps during COVID, our robots might, from those reactions, turn out to be a bit more gentle and a bit more eager to give leeway, while once Corona is over and we get closer again, they might become a bit more dominant again. So I think actually the answer will be, we really need to stay alert and figure this out through the interaction rather than pre-deciding on it.
Yeah, so I can imagine also that we might actually get something like a social optimization problem that which will change dynamically in time, so that the optimal strategy for the robot and the humans will change. It's about being optimal in the movement of basically all actors involved.
Yes.
Okay, cool. Thanks.
Yeah, if there are no more questions, I would like to follow up on. Oh, sorry, Jens, I was there first. So yeah, I'll just follow up quickly on Simeon's point. So about the dynamic nature of this kind of interaction, which we do not know for sure yet, but we could foresee the way it would evolve, right? And my question relates to basically, what do you think would be the right way of trying to anticipate what these dynamics would look like? Given that, for instance, in some settings, it would be relatively safe, for instance, to just put the robot out there and measure how it interacts with humans and see how humans' behavior responds in to that robot sections, and then how the robots adjust their behavior in response to humans. So that kind of that approach of putting the robot and humans in the wild and just studying how they co-adapt, that is one approach, right? But then the second approach, which could be, for instance, more suitable for situations when it might not be so safe to put them in the wild, the real humans with real robots interacting. You could think, for instance, of autonomous vehicles. The second approach would be to do the same thing, exactly the same thing, just in a simulation. If assuming that we have a really, really good virtual humans, models of virtual humans, which we could use to test our autonomous vehicles, or for that matter, any other robots with kind of significant implications, then there is this fundamental question of whether it will generalize from the simulation, however advanced it is, to reality, to real human-robot interaction. And then where would you put yourself on this kind of spectrum from, let's say, studying behavior in the wild versus trying to generalize from virtual testing? Or maybe there is something else that you have in mind here.
Mm-hmm. I think I'm going to split my answer in two bits. Firstly, I think it's very important to realize that, yes, it's very cool what I'm arguing for, and we want to be responsive and back and forth and all those interactive bits. Of course, that's not the whole deal. We cannot just throw a robot out there and just have it respond to people's facial reactions and hope for the best. So I am not arguing we should abandon everything that's been done so far in social navigation on predicting people's paths and using that to think ahead a bit. In fact, I think we should probably end up with combining them because I think they will strengthen each other, where we can find the paths as we go. But we also predict sort of in the rough strokes where we want to do, and we might at a crossing with a lot of people decide, oh, we're gonna cross mostly to the right, and then figure out the details of crossing mostly to the right as we go. So in a practical sense, where I think the end solution will end up, it will be very much in a mix. That's part one of my answer. I think the second bit of my answer is I think simulations are a very good tool for those kinds of predictive models, where you are trying to train your model to basically get a feeling for how humans will react in those situations where you can predict how they will react. But I think that actually the problem with models, all those things, is that they are limited. They are firstly limited by the ones making them. But secondly, they are also limited because of the question just asked by Simeon, I think. People will adapt as they go. So even if you have a perfect model, hypothetically, I don't think it's possible, but say we have one, the fact that people will respond to the robot and change the way they act over time will mean that the mere fact that you have introduced the robots will make your own model invalid. And I think it's a very good approach to get those generalizing models, but I do think we need this bit of extra interaction to fine-tune the actual last bits on the street. I hope that answers your question.
No, not completely, but yeah, I'll leave it to later discussions if we have time for that. Yeah, I think Jens has the next question.
Thank you. So my question also goes a bit in the same direction. You were talking about the interaction and the back and forth. So I was wondering about how much you want to go into theory of mind and these kind of things.
Yes. I hope you all forgive me for giving slightly longer answers, but I really have a really cool anecdote about this. So I'm gonna just share it with you. So back in the days when AI was mostly symbolic, there was this big problem of common sense. So common sense is the idea that I know that you know that I know that you know that I know that the sky is blue, and at infinity. So this turned out to be quite a big problem, because since it goes to infinity, that poses quite a big problem for all AIs to prove this all the way down the rabbit hole. And actually, I think there's like a decade of people publishing papers struggling with this, struggling with how can we actually prove that something is common sense, that we all know that the sky is blue. Until at some point, there was this really cool paper by Jered and Pickering, where they said, no, wait, let's turn it around. And what they did is they assumed, in fact, that everybody knew all things common sense. So they would assume that everybody knew the sky is blue. And then from that, look when errors popped up. So starting from the assumption that everybody knows it, and then just looking for feedback that shows you have been wrong. And if that's the case, you try to fix it, tell people, oh, you didn't know, sorry, the sky is blue. And continue assuming that they know. And I think that's a really cool story, both because it shows that other people wiser than I have been working on this as well. But also, and now I get to your question, because I think it shows theory of mind is very interesting and rich, but to implement it in AI gives you very big problems, actually, because there's this whole complexity of actually modeling what someone else knows, especially if what they know also involves what you do, and that whole back and forth. So I definitely think that theory of mind is relevant to understand what's going on here. But to implement it, I really like something more similar to the approach of Jered and Picking, where we say, let's just assume everybody knows what's going on here and correct ourselves as we go. It's a bit of a windy answer, but I hope it works.
Thank you.
Yeah, again, I'm just I'm eager to contribute to the discussion, but if there are any other questions, I would just give way. So let me know. Yeah, I'll go for now. So yeah, following up on the theory of mind kind of problem that you see there, have you considered looking into more kind of game theoretic approaches where they kind of nicely avoid this problem of infinite kind of levels of hierarchy for reasoning about each other's actions by just looking at the kind of equilibrium solution, which would assume that everybody has perfect knowledge of each other, and then they would just converge to a situation which is good for everyone in one way or another. And then you could just basically try using some kind of a Nash equilibrium, operator equilibrium, and make your robot follow that, and then hope for the best, as you say you would do, that kind of theory of mind setting.
Yes, and I think this is actually quite a similar question to your previous one, where on the one hand, we definitely don't want to just go into situations of social navigation blindly. We want to be able to predict a bit of what's going on, to make some assumptions, and start with a good guess. At the same time, as I unfortunately learned when playing games with other people, most other people are not that optimal in their decisions. Me neither, by the way. But so there is this. Yes, I think game theory is a very good starting point, and it's very rich. But I think also when you throw this into the wild and into the real world, there will pop up situations where people are less perfect or predictable than you would hope. And I think that what I have been proposing might be a way to handle those specific situations, the situations where game theory breaks down because people are imperfect, could have a bad mood, could have any reason not to obey your predictions.
Okay, thanks. Ruel has a question.
Yes, thank you. Thank you, Jered. It was an interesting presentation, fascinating topic. I'm kind of building on a few people here, including the last from the last question or last answer. Some of my former colleagues in Berkeley, they developed kind of a way to interact, robots with pedestrians based on a technique called reachability. Probabilistic reachability, where you basically have a game theoretic approach, and you have some kind of model for human pedestrians, and you're predicting their most likely paths, and you're trying to navigate yourself around those. And when, of course, perhaps different pedestrians can have different parameters and have different, form different predictions. And when you see behavior that is doesn't align with the models that you have, what you do is you use this technique called reachability, where which is used to kind of figure out how to stay in a safe operating zone. You use that in a dynamic sense. So what happens is the safe zone basically would, let's say, shrink if you have some behavior by a pedestrian that you're not familiar with. So you're going to be more conservative. You might slow down at that point, and you might want to kind of update your models. And one of the critiques with that is that it can be quite conservative, or it can be quite easy to become super conservative and kind of stop, right? And that's the moment where you either want to collect more data or make your models better, or you want to say, you know what, in these moments, there's so much uncertainty in my model for me to stay safe that I want to interact. So I think there's a really nice kind of complement. That's a really nice paper, I think. The paper's called probabilistically safe robot planning with confidence-based human predictions. And my question is, would it be interesting to see like when that technique kind of breaks down or becomes too conservative? Like what kind of cues, what are the kinds of cues or kinds of interactions that you want to design to, bring those two worlds together that you were just talking about? So just an idea, and I'd be happy to discuss that offline if that's of interest.
Very cool. Yes, and it sounds like indeed it would be a very good indicator of when it is a good moment to switch to more of the interaction and more looking into it. Yeah, I think that's my main answer. Yes, it sounds like a very interesting thing to look into, and I'll definitely be looking back into the YouTube video to see, or the recording to see what you said, and then look up that paper. Very interesting. Thank you.
Yeah. So maybe like I have a dog here that's about to bark. Sorry about that. Seeing something. She's trying to update her own model, so what's safe or not. Yeah, I guess my question, or maybe like the prompt, is like, yeah, how do you, like, what do you use as the context of designing social cues? And I think using other techniques is actually, I think, can be a very rich place to be creative about like what are the kinds of social cues you need. So that's maybe also a question whether that's like how you think about that.
Good. Yes.
Yeah.
I think, and to relate it to the situation. So when we get in the situation that people don't correspond to our models, I think what we are most interested in and should be most interested in is how they relate to us. And I think that's actually the cues that I would be most interested in. So I already mentioned one. So for example, when someone is testing the robot, challenging it by adapting their path so that it actually becomes a run-in. But it could also be more subtle things like people really actively avoiding eye contact with the robots or looking to a robot and being a bit more scared. It could be a big smile where people are seem to be very enthusiastic and eager, which for many robots is a good thing, but not for most delivery robots. And I think that means that the main cues will be indications of how people might be feeling towards the robots, because I think that will be the most informative for making it decide how to respond differently to those people from what it would normally do.
Thank you.
Can I follow up on the social cues question? I mean, it does sound very promising, and I could realize how this could be useful. And at the same time, when you mentioned facial expressions, it feels a little bit like a slippery path here, because yeah, there is quite a lot of research recently that is showing that detecting emotions and internal states based on facial expressions is not reliable at all. So it has very high individual differences, and it is a slippery slope. So there used to be this this article. What was it called? It said something like AI emotion recognition can't be trusted or something like that. So yeah, what would you think of that? Because yeah, if a person smiles, it might indicate that they have a positive kind of attitude towards the robot and they want to approach it, or it might indicate that the guy is just saying, "Oh, I hate this robot," but it would look like a smile, right?
Yes. I think I can say two things about that. The one thing is, my guess would be that the cues to start with are not facial expressions. You need very high quality cameras that don't have the range that you can use practically when driving a robot around. So I think a much better starting point in this specific context would be things like trajectory, body pose, those things. That said, my guess would actually be that one of the reasons those problems arose with facial expressions is that we don't use facial expressions just to express our inner world. We use them to communicate. So if someone is smiling at me while I'm walking on the street, that might not mean at all that they're happy to see me. But it still signals something to me. And it might still mean that they are okay with me getting closer to them while we're crossing the street. So I would say that I completely agree with the new ideas that facial expressions are not meant just to express our emotions and internal states. But I actually think that's they are meant, I think, to communicate to other people, to somehow make them aware of something. And I think that communicative meaning of facial expressions and all kinds of social cues is actually what we are interested in this case. More than trying to understand the underlying emotions of or internal states. So that's, I think, the two sides of it for me.
Right, okay.
Thank you. Any more questions? Thoughts, suggestions? I don't see any hands.
Yeah, no hands raised. Did you mention that you also wanted to share something else in the end of your presentation? Or we wrap up at this point?
I think actually this is a better point to wrap up.
Yeah, okay. Yeah, if you're curious, I think Roel posted the link to the paper he mentioned. I also posted it a minute earlier, and then Derek posted a link to another paper. So check out the chat for the links. Yeah, if we don't have any more questions, then thanks, Jered, for the really nice talk, and the discussion was really lively, and I enjoyed it a lot.
And thank you all very much.
Oh wait, we do have a question.
I have a final question. Just a final one, okay? So I was thinking about these different things that were discussed, about like game theory of mind, a lot of different interesting approaches to do this. But are we considering a specific goal for the robot, for the mobile robot? The goals of the robot is to go from point A to point B as fast as possible. So are you assuming some kind of things? Are you some kind of goal of the agent, of the robot itself? And if that would be the case, wouldn't he just push like what kind of social cues to use? Wouldn't the robot just say, maybe if I just a pushy person, I can imitate this kind of person that really push everyone, arrogant, I don't care about anything. That would be the best thing to do, given my goal. So how do you see these, and how do you see these within a kind of a machine learning framework that could be learned, this kind of social cues can be learned and can be used for a given goal? How do you see this? And please share your thoughts.
Honest answer, I would be super happy if we could get to the point where we can make a horribly pushy robot. So if we sort of got to that point of understanding, where we know, okay, so this is how pushy people on the street manage to actually walk this quick and get people to move out of their way. That said, of course, I don't think typically the goal for these kinds of delivery robots is on the one hand time efficiency, so be quick in their deliveries, but on the other hand also to fit in and not offend people and sort of be sufficiently socially appropriate. And that would ideally result in a robot that's not fully pushy, but that can be pushy if it needs to be. That can, if a bunch of teenagers is harassing the robots, can say, okay, wait, I'll switch to my pushy mode and I'll take my way through this bunch of horrible teenagers and get where I need to be. I think we need several different behaviors, and I think that's logical because we have several different things we want to optimize. I hope that sort of answers the question a bit.
Yeah, just as a quick follow-up on that, and who decides that? These goals, these objectives. I know there's a lot of different ways to do, but who should decide that? That's also, there's no right answer, but just about how to do.
I think I'm going to be
right?
I think the answer here is that this is one of the reasons I'm super happy that I'm at the design faculty now.
Yeah.
I still have very much of an engineering mindset. I'm just trying to figure out optimal solutions. I'm still trying to model this whole interaction stuff. And I think that actually the amazing thing about designers is that they somehow often find or know how to find a balance in this. How they do this, I'm still figuring out myself. Perhaps they don't know themselves explicitly either. But I do think that's one of the reasons it's really nice for me to be at a design faculty and to see how they figure out that balance between the different needs and requirements.
Yeah. Great, cool. Thank you very much.
Thank you.
Yeah, with this ode to the designers, I guess we wrap up today's talk. Thanks, Jered. Thanks again, and thanks everybody for the discussion. See you next week. Oh, wait, we don't have a meeting next week. So the next meeting is in 2 weeks. Yeah. And then we will have Javier Alonso representing about multi-robot navigation, I guess, which is actually related to what Jered was talking about today. Okay, good. Bye-bye.
Thank you.